Assalamu alaikum, I am Abdul Muqeet and I am back with another lecture of our course, that is DSP Digital Signal Processing. In previous video I told you about what is FFT and how we can use it to reduce our computational cost. So today our lecture is sampling theorem. So it's a very important topic in sequencing systems. So what is sampling theorem? Basically, sampling theorem can be defined as you can say the conversion of an analog signal into a discrete form by taking the sampling frequency as twice the input analog signal frequency. So basically what we do is we take the sampling frequency as twice the original frequency. So that's the sampling theorem. So let's suppose we have a signal over here and we want to multiply it with a pulse train. We're going to get a signal like this, a discrete signal over here. Suppose we have a signal x of n there. We're going to find the DFT of this signal. We get this. You know how to find the DFT. So what will happen, let's say what will happen if I delay my input signal? What will be the effect on its DFT? So when let's prove it. We're going to delay our signal. As you can see, one was x of 0, now x of 1 is 1. And others are same. So what we're going to do, we're going to find the DFT over here. We're going to use the same formula as we're using the previous videos, and when you find it you get x of k over here, that is this. So the difference, as you can see, that the first value will remain the same and the other values will change with a exponentially with the with a difference of pi by 4. And let's suppose we doubled our delay by 2 times. So now when first in first our x of 0 was 1, then we calculated its Fourier transform, and then we delayed our 1 at x of 1, and then we find and we saw that there was a difference of pi by 4. And now we're going to delay it by 2 times, that is x of 3 is 1, and then we're going to find the x of k. So when we find this we get values like this. So what is happening over here is basically that when there was a one time delay, there was a difference of pi by 4, and when there was a 2 time delay, there was a difference of pi by 2, and it will keep on going like this. So it was necessary to tell you that what will be the effect of delaying your signal, uh, uh, um, and what will be its effect on its Fourier transform. So here is that effect, and let's talk about convolution. Why we do convolution as base? Convolution is convolution is basically what you do in convolution is you can say convolution, it's an operation function that produces a third function expressing how the shape of one is modified by the other. So that is convolution. And in signals and systems we say that we what is the effect of two signals is to get a third signal. What will be the effect of one signal to the second signal, so that it can create a third signal. And how we do convolution is basically what we do in convolution is that if you have two signals, what we do is that we basically we basically what we do in convolution is that if we have two signals, we're going to mirror one signal and then pass it through the second signal by multiplying it. So that signal that we get will be the convolved signal of those two signals. And there are many methods to do convolution. One is the tabular method, second is the graphical method, third is by using formula. We have all that, but here I'm going to tell you a shortcut of convolution method. how to do convolution. So if you have two signals and you want to convolve them, what you're going to do is write one signal like this and the other signal like this. It doesn't matter what place you choose. I could have brought x of n over here and delta of n over here, but it will give the same result, so you don't have to worry about that. So what we're going to do is, well, similarly just we're going to multiply these values, that one zeros are 0, 1 with 1 times 1 is 1, 1 times 0 is 0, 1 times 0 is 0, and 2 times 0 is 0, 2 times 1 is 2, and similarly we're going to find all of these values. And the next step what we are going to do is that we uh, sum the diagonals. We're going to sum the diagonal values. So 0 will get 0, 0 plus 1 it will be 1, 0 plus 2 plus 0 it will be 2, 0 plus 3 plus 0 plus 0 is 3, and similarly we do the same. And we're going to get these zeros over here, which we're going to neglect them. So that is the convolved signal. So that is how you find convolution. So what the main method is, the main method is that you take a signal, you mirror that signal, and then you pass it through the second signal, and the output will what you will get, the output is the convolved signal of those two signals. And there are methods like tabular, graphical, but I have done the shortcut method over here. You can use it, it's a time saving method. So main thing, now let's get to the main thing, the sampling theorem. So what is I have told you what is a sampling theorem, and so but why do we need it? uh, it is a theorem, but why do we need it? So here's the reason why we need it. Let's suppose we have input signal, that here it is. I have taken a random input signal, and let's suppose we have the output, the modulated output signal. You can say like it might be DSBSC signal, you can say modulated signal. We have this. So now at the receiver side, we're talking about communication. At the receiver side, we want to get the original signal from this modulated signal. What we're going to do, obviously we're going to demodulate it and then pass it through the low pass filter. So what will do, the demodulation, in demodulation we're going to select this, and in low pass filter will make like this. So we're going to select this signal to this. But as you can when we modulate a signal, its frequency is so its frequency is, its amplitude is reduced, and uh, so if we want to get the original signal, we want our sampling frequency to be greater than 2 times of the maximum frequency of the input, yeah, or original signal. So if we don't do that, let's suppose we took our sampling frequency, let's say equal to fm, let's say, then what will happen is that we're going to get the overlap. So basically what is happening over here, this is the overlap of these signals, and this overlap is called aliasing. What happens is that this overlap, aliasing, is that it smoothens the frames, and this is actually, we don't want that. Just take it that we don't want aliasing at all. So to do that, our sampling frequency must be always greater than twice the maximum frequency, or you can also name it as oversampling. What you do is oversampling the signal. So when you do that, we get like this. So then you can easily use a low pass filter to get the original signal. So that is what a sampling theorem basically is that we all